Simple harmonic motion, I think probably the two easiest things to look at first is just a mass on a spring with no friction, and then a mass on the end of a string oscillating back and forth like a little pendulum. So from an energy perspective, the energy at any single point here can be expressed as a 1/2 kx squared plus a 1/2 mv squared. When it's fully stretched, well, it probably has all elastic. As it's fully stretched and then comes back to equilibrium, when I say equilibrium in this case, I'm talking about the masses at the natural length of the spring, so it's not stretched or compressed. Well, then all the energy is going to be kinetic, and so it goes back and forth. So this thing is also then equal to 1/2 ka squared, where a is the maximum x value. It's a because it's the amplitude of the motion. Or we could say that's also equal to 1/2 mv max squared, because it's all kinetic, right? All elastic occurs when x is equal to a, and all kinetic occurs when x equals to 0. Okay, and again, this goes back and forth, and then when it's midway, or 3/4 of the way stretched, well, then it's got some elastic and some kinetic, and there's a give and take between those two quantities. But the extremes, fully stretched or fully compressed, and in this case it's at equilibrium, and it's got all of this. If you look at the pendulum, it's this give and take where the energy is all either gravitational potential energy or kinetic. And again, this thing just swings back and forth between this side, straight down. Again, when it's straight down, it has no potential, and it has all kinetic, and it goes all the way up and stops, but when it stops, it has no more kinetic and has all this. So again, it's this interplay between both of those things. We can remind ourselves that H is equal to L minus L cosine theta. And again, we've done that geometry quite a bit. Okay, so now let's look at the equation of motion. The equation of motion, again, our whole goal here in this particular case is to find x of t. To find an equation that models the behavior, meaning the motion of this mass, as a function of time. Energy can tell us how fast it is at any given position, but it can't tell us when it is at a certain position. And then over here, we're going to find theta as a function of time. Okay, so on springs, we just start out with F equals ma. The force is negative kx. There's no friction, so that is the only force. When I say only force, I mean only force that we care about. Certainly there is still gravity and a normal force, and in this case, we'll put the spring force. And again, we know that the spring force is equal to negative kx, and that's equal to m, and then instead of the acceleration, I'm going to write x double prime. The second derivative of position is acceleration. I'm going to go ahead and divide by m, and I'm going to get this differential equation. Now, this particular differential equation that I've boxed is a second order, and it's a second order differential equation because it's an equation that relates the function to its second derivative, and it's a non-separable differential equation, which means we can't use the calculus techniques that we typically learn in like a Calc 1 or Calc 2 class. Now in class we discussed that this particular differential equation, as long as it's in this form, will always be solved by a cosine or a sine curve, and that we can write it like this: cosine of omega t, where omega is the square root of this factor. And again, you can think that through. We're looking for a function and yet a function, so when we take two derivatives, we get the opposite back. Right? The second derivative is the opposite of the function. Well, the second derivative of cosine is going to mean negative cosine, but we also create this factor. And again, if you take two derivatives of cosine of omega t, you're going to get omega squared out in front. And so this thing is omega squared, so then omega is k over m. But if omega is k over m, that implies that the period, well, we know the period of a trig function is 2 pi over omega, so that means the period is 2 pi times, Right? Dividing by omega is just flipping this, m over k. Now we have an equation of motion, and we actually have the equation for the period of a pendulum. Now we can look at this motion. The motion x of t looks like some cosine curve, something like that, where this particular point is fully stretched, and then this is when it gets back to equilibrium. This is fully compressed, back to equilibrium, and back to fully stretched. And this time period represents one period. Right? One period is the time it takes to do one complete cycle or one complete rotation. Okay, and we have an equation for that, and the period is a function of the mass and the spring constant. If you increase the mass, this equation says you're going to increase the period. If you increase K, which is the stiffness of the spring, making the spring stiffer, you're going to decrease the period, which I think, follows some common sense. All right, now let's look at a pendulum. A pendulum is going to be this exact same thing. Everything is identical except I'm going to start with torque equals I alpha. The torque on this thing, we'll think about the forces here. The force that we're looking at is mg. There is a tension, but that tension is directly back to the pivot, so it doesn't cause a torque. Thus, the torque is negative mg L sine theta. L sine theta is my lever arm. That's this distance, right? Horizontal distance for a vertical force. I for a pendulum is ml squared. And then alpha, we're going to write as theta double prime. Just like over here, we took A and wrote it as x double prime. I can cancel these m's. I can get rid of that L and one more power of L. And what I need to do here is the small angle approximation. For small angles, sine theta is approximately just equal to theta. That's a Taylor series expansion. So if you haven't had BC calculus or Taylor series, you may not fully understand this, but we did look in calculus at the beginning of the year. We looked at the limit of sine x over x as x goes to 0, and we showed that those are the same thing. Oops, not 0. That's equal to 1. And what happens there is, if you look at the sine curve, and you look at the curve y equals x, as long as you're pretty close to the origin, those two curves are the same. So we basically just replace that. And then when we replace that, we get negative g divided by that L, and then instead of sine theta, I'm going to write theta equals theta double prime. And I'm going to box it, because now these boxes are the identical form. Negative some factor times theta equals theta double prime is the exact same pattern as over here. Well, if we've proven that this is the equation for this differential equation, then we also know that theta of time can be expressed as some amplitude. In this case, the amplitude is some like maximum displacement times cosine of omega t, where omega in this particular case is the square root of g over L. But then that tells us that the period, for the same reasons, is 2 pi divided by omega. Dividing by omega is then L over g. And this also makes sense. This says that the period increases with the length of the pendulum. Okay, make this longer, takes longer to swing, and decreases if I strengthen gravity. So if you go to like Mars where gravity is stronger, then we're going to actually decrease the period. So I've derived both the equation. I found x of t and theta of t for both a mass on a spring and a mass on the end of a string. They are very similar in terms of how they work. And let's do a little calculus cleanup here. If this is my equation for x of t, then I can take the derivative of that and get the velocity as a function of time. The derivative of that is negative a omega sine omega t, which a negative sine curve is going to look something like this. And that matches up perfectly with what we think over here. Think about it. When I'm fully stretched, this point here corresponds to this point here. Velocity equals to 0 when I'm fully compressed. Velocity equals to 0 when I'm fully stretched. Velocity is at a maximum when I'm at equilibrium. Equilibrium, maximum velocity, just headed in the other direction. Velocity of 0, fully stretched. These 5 points match up perfectly with the other 5 points. And then if we take the derivative of again, we get the acceleration equation, which is negative omega a omega squared cosine of omega t. And then we can draw a negative cosine curve, which looks like this. And it says the exact same thing. When you're fully stretched, which way you're going to accelerate? Bingo, negative acceleration. Because when you're fully stretched this way, pull it this way, and release it, you're going to accelerate left. And you're going to have your biggest acceleration when you're fully stretched. As you become less stretched, your acceleration goes down as well, and that's why, again, they're opposite of each other. The acceleration is always opposite the position because the force, Hooke's law, the force is always opposite of the displacement, and it's proportional to the displacement. And again, you get these three equations once you know x and v and a. You also can find the maximum velocity. It's right here. That number is the amplitude of the new trig function. This is the maximum acceleration because it's the amplitude of this new trig function. You can get all sorts of things when you look at just these real topics.